Our project is schema-guided IR plus deterministic compilation, a neurosymbolic pipeline for structural logical reasoning. I'm Xiaoqi, and I'll be presenting the first half with my partner Xinran talking over the second half. We study the problem of translating natural language into executable symbolic program. Reason neurosymbolic system, such as logic LM, program of thought, use LLMs to generate programs and execute them with symbolic solver, enabling more reliable and verifiable reasoning. However, this pipeline is highly brittle in practice. There are two major failure modes. First, parsing errors, where the generated program has invalid structure. The generated program is phonetically malformed at logic language level. It equates a level value expression with an existential Boolean formula, so the parser cannot build a valid internal representation. Second, execution error, where the solver failed due to ill-formed constraint. The program is phonetically close enough to be parsed, but it failed during execution. The implies is given 3 arguments instead of 2, which is not a valid executable solver expression. This suggests that the core issue is not semantic understanding, but the difficulty of generating structurally valid formal program from natural language. Prior work showed that large language models often struggle to generate structure valid formal representation, even when their semantic understanding is correct. This leads to high rates of parsing and execution error. While self-refinement methods can partially reduce these errors, they remain unstable because they rely on unconstrained regeneration. Neurosymbolic method generates programs from natural language and execute them with solver, enabling verifiable reasoning, but they rely on brittle direct generation. Syllabic parsing provides a general framework of mapping natural language into formal representation, but it is difficult to ensure structural validity. Constraint generation method introduce grammar or schema constraint, which improve semantic correctness, but are not integrated into a full executable pipeline. Finally, self-refinement methods iteratively improve outputs, but remain unstable because they rely on unconstrained regeneration. Overall, existing approach either depend on brittle generation or unstable refinement and lack a unified mechanism to enforce structure correctness. To address this, we introduce a schema constraint intermediate representation to enforce structure and use deterministic compilation to guarantee executable programs. Our approach separates the problem into 5 stages. Instead of asking the LLM to direct generate a fragile logic DSL, we first let it produce a schema-guided IR. This IR is a structured format such as JSON. Next, we validate the IR to check whether it's complete, type consistent, or structurally legal against a schema. Then we use a deterministic compiler to translate it into domain-specific language. Then C3 solver executes it and returns the answer. 3 design decision matter here. We use IR instead of direct DSL because LLM produce inconsistent DSL syntax, but a schema-validated JSON is far easier to constrain and check. Compilation is deterministic because once the IR is valid, the output is fully determined without hallucination at that stage. And we use Z3 because it can probably answer whether a formula is satisfiable, valid, or unsatisfiable. Our research has 2 main contributions. First, we designed the entire IR schema from scratch, including all the constraint type, entity structures, ask type, and the validator. This covers the full range of reasoning patterns in datasets. The key point is the separation of responsibility. The LLM extracts, the schema validates, and the compiler converts. The contribution of schema and the compiler architecture results in a drop in parsing error by over 60% on both datasets. The second contribution is single-pass IR recompilation. When IR extraction fails, instead of randomly retrying, we do structured failure recovery, classify the failure mode, reparse the natural language to recover missing constraint, generate a corrected IR, and recompile. This is a principal repair mechanism, and it further improves accuracy beyond schema-guided alone. We use few-shot prompting to guide the LLM IR extraction, and there's a specific reason we choose over zero-shot or direct JSON. Research has shown that forcing LLM to output strict JSON during reasoning and actually hurts performance because the format constraint interfere with the generation process. Few-shot examples get around this. Instead of telling the model what format to use, user shows it. Each shot in our prompt is a complete problem to IR mapping, so the model learns the schema structure from example. There is no fine-tuning, no format enforcement, just demonstration. The right side of the slide shows our actual prompt structure, a system instruction followed by 4 example problems, each paired with its correct IR output.
Show an example of our pipeline. The input is a natural language local sharing problem. Instead of generating executable DSL directly, the LLM first produces a schema-guided JSON intermediate representation, or IR. This structured IR explicitly separates entities, constraints, and question type. For example, the every mass shear field captures roster-style constraints that are difficult to represent in traditional fixed schemas. Most importantly, the IR is validated before compilation. If the structure is malformed or incomplete, the validator catches the error before anything reaches the solver. Once the IR is validated, it goes through a deterministic compiler. The compiler converts each IR structure into executable Z3-ready DSL code. For example, every mass shear expands into multiple mass shear constraints, while ask type determines the corresponding solver query. Because this stage is fully deterministic, the same IR always produces the same compiler program, eliminating LLM randomness during execution. When IR extraction fails, we trigger a structured recompilation process. First, we classify the failure type. In this example, the IR is empty, meaning the model failed to extract the problem constraints correctly. Next, we return to the original natural language problem and recover the missing entities and constraints directly from the text. Finally, we generate a corrected IR and send it back through the same deterministic compiler and Z3 pipeline. So instead of retrying generation blindly, recompilation performs targeted structure recovery to improve executability and robustness. Here is another example from our data. The question asks, if both types of jazz are on sale, what is the minimum number of new CD types included in the sale? The gold answer is option A. On the left is the baseline. The LLM generates DSL directly, but the generated program does not correctly capture the minimum semantics. The Z3 solver fails and produces no output, so the system falls back to random guessing A as the answer. The label happens to be correct, but there's no verification behind it. On the right is our pipeline. The model first produces a structured IR that explicitly represents what's selected and what the question is asking, specifically a minimum count query with value 1. The deterministic compiler then converts it into a precise solver check. Z3 confirms A is true and other options are false. Both pipelines output A, but only ours get theirs through valid reasoning. We have 3 main research questions. First, whether schema-guided IR generation improves executability over the logic LM baseline. Second, does schema-guided IR improve final answer accuracy over the logic LM baseline? And third, whether recompilation provides additional gains beyond schema guidance alone. For evaluation, we use 100 samples each from the AR, LSAT, and folio development sets. We compare against the Logic LM direct SL generation baseline using Q1 Turbo for IR extraction, Z3 as the solver, and our deterministic compiler pipeline. We evaluate the system using 4 metrics: accuracy, parsing error, and overall success rate, allowing us to measure not only answer quality, but also whether the generated reasoning process is actually executable and solver valid. Starting with overall performance, we see consistent improvements across both datasets. On AR-LSAT, accuracy increases from 29% in baseline to 33% with schema-guided generation, and 34% after recompilation. Folio shows a similar trend, improving from 25% to 29%, but the biggest improvement is in parsing reliability. For AR-LSAT, parsing errors dropped from 24 to just 5 cases. For Folio, they decreased from 29 to 9. This shows that schema-guided generation produces much more executable intermediate representations, while recompilation further improves robustness. We also achieve 90% IR validity on both datasets after recompilation. Overall, these results support all three research questions. Our framework improves executability, reduces parsing failures, and consistently outperforms the logic LM baseline across both benchmarks. So to wrap up, our main finding is that separating LLM generation from deterministic compilation makes the pipeline verifiable. Instead of hoping the LLM gets it right, we validate the structure first and only send well-formed programs to the solver. That's what drives the improvement. For future work, three things we'd like to tackle. One, extending the schema to handle more complex constraint patterns we haven't covered yet. Two, make the repair step smarter. Right now, it's a single pass fix, but ideally, it would now exactly know which type of constraint failed and repair that specifically. And three, tracking more fine-grained metrics so we can better understand where the remaining errors come from. And that's all. Thank you.